collision because it's two molecules banging into each other, right? If there are three, it'd be a trimolecular. Usually don't get more than three because the chances of four things banging into each other in the is infinitesimally small. So you usually see a unimolecular, bimolecular, or maybe a trimolecular at most. The second step, C, the product of step A, bang into substance D to make E. Then in the third step, E bangs into another molecule of A, another bimolecular elementary step, to produce F and B. That is the third step. Now, some of the things in that reaction mechanism are intermediates and some are catalysts. And we can see which ones could possibly be those things by seeing which things cancel out, essentially. If you were to add the reactions up, like you're doing algebra, where you're adding algebraic equations with x's and y's, right? So if you're very careful about this, okay, I'm going to circle all the things that cancel out first, because they're not going to end up down below. There's a C on the right. There's a C on the left. That's neither an intermediate or a catalyst. There's an E on the right and an E on the left. That's either an intermediate or a catalyst. There's a B on the left and then there's a B on the right. That's another one. The only things that don't cancel out are the two A's on the left, the one D on the left, arrow, and the one F on the right. And that is your overall reaction. So even though C and E and B don't appear in the overall reaction, they do participate in collisions and therefore are part of the mechanism. All right, let's identify our intermediates and our catalysts first. Intermediates are something that's made in one step, and that means it's a product. It's made in a step, it's a product, and then it is consumed in a subsequent step, so later on it shows up as a reactant, and that's why it cancels out. So it always shows up first as a product, something that's made, and then it is consumed, okay? In the potential energy diagram, right, you can think of this as like, this is like step number one is occurring here, right? And down here, we produce some sort of an intermediate that's down here at the bottom. That's not the same as the activated complex, right? And then there's some other intermediate that's over here, okay, at the trough here before we get to the last step in the mechanism, right? Each of those hills represents the activation energy of each of the individual steps. So there's an activation energy for step number one, an activation energy for step number two, and an activation energy for step number three, okay? And the activation energy goes from the plateau up to the top of the hill. Sometimes the activation energies are larger values, which means those reactions are going to be slower. Okay, so let's find our two intermediates, right? Letter C is an intermediate. Why? Because it is made in the first step and then it's consumed in the second step. E is also an intermediate because it is made in the second step and then consumed in the third step. Intermediates are basically products first, and then you're going to see them as reactants. Catalysts, on the other hand, are going to show up as reactants first, and then they're going to show up as products, but they're also going to cancel out. So B, which is a reactant, when it collides with A to make C, but eventually it gets produced or reintroduced in a subsequent step as a product. So B is a catalyst. Now, so bottom line, intermediates, products first, then reactants. Catalysts, reactant first, then products. And just to remind you, the catalysts are always placed in an equation on top of the arrow. Intermediates show up nowhere in a reaction, okay, in the overall reaction. But catalysts will be placed above the arrow, indicating that they're critical for the reaction, okay? And we can talk about what step they participate in as well. Okay, so we know catalysts speed up reactions, right? So what they're going to do is they're going to affect what's called the rate determining step. Now, just to go off on a stupid analogy to make this clear, if something happens in multiple steps, it is the slow step that determines how fast the overall reaction occurs. And let me make it real simple. Let's say you're going to Target and you decide to buy three things at Target. You're going to buy a t-shirt, white, simple. You're going to pick up some dog food, right? And you're going to pick up some Apple earbuds or some technological piece of equipment, right? Now, obviously, getting the dog food is going to be fast. Getting the t-shirt is going to be super fast as well. As a matter of fact, while you're waiting for the guy to help you get the earbuds or whatever else out of a glass case at the back of the Target, you could go and shop for the other two things just while you're waiting. Clearly, getting that one thing is the thing that determines how much time you spend at Target, right? If you just had to get the socks and the dog food, you'd be in and out like that, and that would be it. But because you have to wait for the guy to open the case and pay it in a separate thing, the slow step determines how fast you get out of the place. That's true for life. It's also true for chemical reactions. And the determining step that's slow is the one with the greatest activation energy. So whichever one has the greatest EA is going to be the rate determining step. All right. Now, what you can see in this diagram okay, is you have three activation energies. The first one, the second one, the third one. It doesn't matter that this is the highest plateau here. What matters is the size of this arrow here. Okay, what this says is EA number 2 is the rate determining step. Because the activation energy is so high, most of those collisions are not going to be effective. That is going to be the slow step. That is the step analogous to going into the target and picking up your computer or something like that. Okay, and that's going to determine how fast the reaction occurs. Unfortunately, our catalyst occurs in step number 1. If you were trying to speed up this reaction, you would try to get a catalyst that would affect the second step. And if you did find one, that would speed up the reaction, because this is the step number 2 here that is slowing you down. So quick summary of what we learned here. A couple of things real fast. Intermediates, produced first, reactant second. Catalyst, reactant first, product second. Rate determining step is the slowest step. It is the one with the greatest activation energy. Doesn't matter how tall the hills are. What matters is the length of this arrow from the bottom of where the intermediate is or the reactant is to the height of the hill, whichever one is longest, is going to be the slow rate determining step, which means in this case, the second step is the rate determining step. You should recognize that intermediates always occur at the bottom of the trough. Activated complexes are at the top. These are the reactants. These are the products. And regardless of the step, the overall delta H in something like this, since the reactants have more energy than the products, okay, this is still an exothermic process, and the delta H is still a negative value because energy is going to be released overall in the mechanism, which means in the chemical reaction, the energy or heat will be on the right-hand side, as it is in any exothermic process. That's a quick review. Again, if the products have less energy than the reactants, it's exothermic. The heat's on the right-hand side. The value for the delta H is going to be a negative value. Okay, so an intermediate is produced first and then consumed in a subsequent step. Catalysts are consumed first, okay, and our product later, okay. They are not. I don't know what I was going to write there, so I'm going to leave that blank. That's all you need to know. I think I did a good job. Hope you enjoyed it.